In this lesson, we're going to prepare to learn and to accumulate facts and figures and see how we can draw a two-column proof. This is a very formal method in geometry. In order to organize our definitions, our postulates, our theorems, and other properties, as well as given clues and other facts and figures, we can develop this two-column proof. We're going to show how we can start with all these parts. We're going to develop strategies, how we go about the proof. And if all goes well, we'll end up with actual proof, and maybe even two actual proofs at the end. First of all, 5 key elements of a two-column proof include the given, which is simply what we have been presented. It's like the hypothesis. It's kind of laid out for us on a silver platter. Here's what we have to work with. That is the given. It may be a certain kind of a triangle. It could be a certain kind of a line or point relationship, or some kind of original given clues to start with. We've got to build upon something. That is the given material to start with. We also have a diagram as another element of the two-column proof. We have to draw the diagram, the picture of it. In other words, it could be angles, it could be triangles or other polygons, or whatever the case may be. But we would draw a diagram that actually describes what was given to us in the first place. And we should try to draw it as close to scale as we can. It doesn't have to be perfect, but it should logically be as close to scale as possible, because that'll help us arrive at some logical conclusions. Then we have what we're trying to prove. We have the given and the prove, the beginning and the end, and the drawing in the middle. What we're trying to prove is actually our final conclusion that we arrive at. The prove is the final analysis, the bottom line of a proof. Then we have the statements on one side and the reasons on the other side in an organized manner. And we try to arrange them, of course, in a logical order and with a frame to go by, a numeration system so we can tell which reason matches up with which statement. And then everything is in a very logical order. So again, we have what's given, then the diagram, we make a picture, and then write down what we're trying to prove here. What are we going after? What's our end result? And then we begin a series or two columns for our statements on one side and the matching reasons on the other side. Let's take a look. These reasons that we're going to use on that right-hand side of our two-column proof can be the given information, the original clue that we would start out with on a search or a scavenger hunt, you might say, our first clue. The given information to start with. We also have definitions of things, points or lines or other relationships or concepts that can also be used as a reason for what we make a statement about. Postulates, which we are beginning to accumulate through these various lessons, and we have a few more to go through. Postulates can be used as a reason as to what we are going to say. Properties. They could be algebraic properties that carry over into geometric properties. Those are also very important reasons that will help us arrive at a logical deduction. And of course, then we have theorems themselves. And theorems, can evolve from other theorems, or they can evolve from previously stated postulates. So these are the various things that we can write down as our reasons in our two-column proof. Again, given information, the original clues, whatever they may present to us. Then we can use definitions. We have a file chart, you might say, a flip file here of information, of definitions, as well as the postulates, the properties, and all the theorems. As we go through these series of lessons, we may take time and prove other things, and we will accumulate more postulates, more definitions, more theorems, and maybe even a few more properties. So we can gradually accumulate more, and the more we have to work with, the easier our proof will become. Let's get into one here and see what we mean here when we draw and label the diagram of a proof. First of all, if we are to make a diagram and they say something in our given about a midpoint, if they allude to the given, or in the given, to a midpoint of a line segment. Then you think, all right, let's make the drawing accordingly. Make a line segment, call it line segment AB, and declare some point, we'll call it M for its midpoint. In other words, in your diagram, draw it according to scale. The clue is there. Just take advantage of it and use it and try to draw it to scale as much as possible. You would not want to draw your midpoint, over here someplace or on this side someplace. It is obviously not a midpoint. It is not in the middle at all. Remember, a line segment has one and only one midpoint. So make it in the middle exactly to scale. And again, like I said, that will help you see what you need to do and what to think next about your next statement. If you're talking about an angle bisector, if that is presented to you, in other words, in a given, this could be another little subtle, hidden, given clue. If you're talking about an angle bisector, then draw the angle involved so it is actually bisected. Let's call this angle COA. And if that's the angle in your drawing, it could be an angle within a polygon, like a triangle or a four-sided figure of some type. But if they talk about an angle bisector, draw it like it is supposed to be drawn. And that means bisect the angle. Try to draw that angle bisector as perfectly in the middle of the angle as possible. Then that would divide this and this into two congruent angles. We'll call them angle 1 and angle 2, and label them, you see. So if this angle bisector is, let's say, ray OB, then you could refer to angle 1 in your proof as angle COB or angle BOC or just angle 1. If you refer to this angle here in your proof, you would just call it angle 2, which could also be called angle BOA or angle AOB. You could not just call that angle O because there's more than one angle, remember, at this point. There's this angle above and this angle below and then the entire angle, COA. So in a case like this, when you refer to this in your proof and write it down, if you're talking about angle 1, then say angle 1 or say angle BOC using 3 letters. The symbol for angle, remember, is this little symbol right here. You may use these symbols to save time and space when you write your proof. We have a list of symbols and abbreviations in our packet, and this shows that this is the symbol for angle. If we have more than one angle, we put a little S in the interior of that angle, like that, and that refers to the word angles. If they talk about, in the given, something about adjacent acute angles. Adjacent acute angles. Well, this puts some words together we've already discussed. The word adjacent means that they're next to each other. They share a common side, as well as the common vertex. The word acute refers to angles that are between 0 and 90 degrees. So, those have to be analyzed, and you think through logically, how am I going to make these angles? Draw them so they are, first of all, adjacent angles, having the same common endpoint, we'll call it point W, and with a common side between them. Now, it doesn't say that there are congruent angles involved here. It doesn't say that the angle has been bisected. So all we know is that they are next to each other. So we could call this angle 1 and that angle 2 separately. Not necessarily congruent angles, but they could be separate, distinct angles. So draw these adjacent angles. You could call this angle XWY, XWY, or angle 1 when you refer to that angle. You could call this angle 2 or angle, let's say, ZWY for that angle. Again, adjacent acute angles. They are adjacent, they are next to each other, they share a common side with it coming from the same original starting point, the vertex, and they are acute, which means they're each less than a 90-degree measurement. If they should talk in your given about perpendicular lines, there are many, many proofs that involve perpendicular relationships. They might be perpendicular lines, they might be perpendicular line segments. But there are a lot of proofs, a lot of facts and figures that we're going to discuss in the future related to perpendicular lines. So again, if they are to be perpendicular, then don't draw them like this, but rather make them perfectly perpendicular at a right angle like this. And when that is a given clue, you might even want to put a little mark in there to tell yourself that they are perpendicular lines. That clarifies they are perpendicular, and therefore they form that right angle. So again, if this is the given clue of perpendicular lines, draw them to look like perpendicular lines. The more to scale your diagram is, the easier it's going to be for you. One other very common fact they might give you is a linear pair. A linear pair of angles. I'm going to use that symbol there again. You see, there's the symbol for angles as a shortcut. That saves space and time. A linear pair. So you think back now, what did we discuss about a linear pair of angles? Well, a linear pair of angles would have opposite sides on a straight line with a common side between them. That's what a linear pair of angles would be. Again, their opposite sides would lie on the same straight line, like this line DB. And then they would have, of course, a common side between them. We'll call this ray EI. So a linear pair of angles are angles that are adjacent. That means they start from the same point and they share a common side, but their outer sides are opposite rays. So angle 1 and angle 2 would be how you would draw a linear pair of angles. In planning a proof, we have, again, remember the 5 parts of a proof. We have the given, we have the diagram or the drawing itself that you want to make, whether it be angles or a triangle or another type of polygon or a circle. We have what we're trying to prove listed, and then you make your columns for your statements and your reasons. So those are the 5 parts totally to a proof. So let's just show a rough skeletal outline to get started with. Let's say we have a triangle here. Call it triangle ABC. And let's drop a line down here from C to hit line segment AB at point D. Okay? That's your diagram. If they tell you have a triangle ABC and you have a line segment coming down from point C in the triangle, that's the way you should draw it, just the way they describe it. Draw your triangle and then draw your line segment down from point C, just as they say. Okay? So that would be your diagram. Then you'll have given facts. Now this is just a general skeletal outline, so we don't have any particular theorem or any point we're trying to prove right here, but again, I want to show you what we're talking about in the previous outline of the 5 parts to a proof. We will have the given facts presented to us. This is presented. This is a clue. If we have this triangle and this line, what can we conclude? Then what we're trying to prove or conclude is the prove. So you get your given, your diagram, and what we're trying to prove. Now we're ready for action. So you make a column for statements, and you make a column over here for matching reasons. Now anybody, no matter how organized or unorganized you are, anybody can help yourself out by simply following this pattern. And it will help you to train yourself to think more logically, more deductively, and arrive at valid logical conclusions. So please try to follow this pattern of thought, and it'll be so much easier as you try to put your postulates and your theorems and definitions all together in the right order. So you number your statements, like statement number 1 and reason number 1 that would match. Now usually the statement would be what is given. We need to introduce the given facts into the proof to start with, so we can develop it from there. So the first statement is usually what is given, and the reason would be that, given. Then statement number 2 often would be your first deduction from this given fact. What can we deduce, or what can we draw from this given fact here? That would usually follow as statement number 2. And then why, with the proper reason. It may be a postulate, a definition, theorem, property. And then on you go. Statement 3 that follows from the previous statement 2 and its proper reason. Then statement 4 and its proper reason. Until you arrive at a final conclusion, what you're trying to prove. Now keep in mind, you have the right to peek back at what you're trying to prove in here. Whatever the facts may be that you're trying to prove, always peek back up here and keep focused on where you're going. Otherwise, you'll lose sight. You may go way off on a tangent someplace, take the wrong exit off of your proof. Get back on the main path and keep focused on what you're trying to prove. So always look back up here with every single step that you go through. And everything will be much more logical, and you will stay focused to the end. Now, some proofs may only take 2 or 3 steps. Some may take 7, 8, 9, or more steps. So there is no particular limit to a proof. It's just a matter of getting it all done in the right order until you arrive at the proper conclusion. Let's take a look at some strategies now for a 2-column proof. Again, this is a formal proof we talked about, a formal 2-column proof. Very nice and structured and orderly. We can learn to help ourselves out once again by using this strategy. We can work forwards from the given clue. That's mainly what we emphasize, and that's usually the way we would do it. Working forward from the given. The given, remember, would be the given clue, the facts we had to start with. Then, what we do is research the list of the geometric facts. Whatever is given, we think, what are all the things we have learned so far related to this given clue? What are the properties? What are any posits or theorems related to this fact? So bring those forward in your file server of knowledge and make them ready. Then find conclusions from each of these facts from the given. Find the conclusions from each fact in the given. So bring these facts forward from your file server and then try to understand what conclusions would they bring us. Then state each conclusion in terms of the diagram. How does the conclusion relate, in other words, to the diagram? Is it relative? Does it help us proceed on through the proof? Will it lead us to something else logically? So again, state each conclusion in terms of the diagram. And number 4, find other conclusions that follow in order from previous conclusions. You may not be able to see a conclusion down towards the bottom of a proof someplace that needs to be inserted in a proof, because some conclusions can be evolved from previous conclusions. That's why it's all very logical and sequential. You won't be able to see down here until you get there. So as you go through the proof with your facts and search for conclusions from each fact, these conclusions will lead to other statements which give us other conclusions. So again, number 1, research the list of geometric facts that we have to work with. Find conclusions, number 2, from each fact in the given. Number 3, state each conclusion in terms of the diagram. And number 4, find other conclusions that follow or that may evolve in order from previous conclusions. That is the process of working forward from the given towards the end of your proof. Another strategy that often works when you get stuck going forward through a proof and you cannot see, where do I go next? What is this leading me to? Am I at a dead end or not? You may work backwards from the prove. What a great idea. The prove is our final statement. That's our final conclusion. So we know what the answer is supposed to be. We know what we have to end up with, what we're trying to prove. That's the bottom line, literally. So we can take that prove and work our way backwards from the bottom statement up backwards. And pretty soon we may connect this proof by working forwards till we get stuck, and then start with the prove and work our way backwards. And pretty soon we've got the entire proof all linked together. Now, when we work backwards, we will not know, of course, how many statements we're going to have in this proof. So don't worry about, oh, what number is this going to be? If I start with the prove at the end as my bottom line, is this going to be number 4 or is this going to be number 7? Well, that doesn't matter. Just give yourself enough room, bring it on down and write it down below someplace, and don't worry about numbering them yet. Then, working backwards, number 1, search the inventory of the geometric facts. Search the inventory of the geometric facts what we're trying to prove, again, backwards. Find the hypotheses needed to conclude what is to be proved. Find the hypotheses needed to conclude what is to be proved. In other words, if we're working backwards, we're really going to be having conclusions, and we've got to think what hypothesis would give us that conclusion. See, we're going backwards here, so to speak. Then, number 3, state each hypothesis in terms of the diagram. See how that relates? Again, remember, keep looking back up to your diagram and keep reminding yourself what you're trying to prove. That way you'll stay focused in the right direction. And number 4, find other hypotheses that allow a conclusion from previous hypotheses, or from the previous hypothesis. Yes. Now, notice here that the word hypothesis is spelled differently in some of these different sentences. That's the reason. That's not a mistake. The word hypothesis, spelled like this, with the I in here at the end, I-S, is singular. That means one hypothesis. By contrast, the plural of hypothesis is hypotheses. I'm emphasizing the letter E there, hypotheses. That's the only difference in the spelling. Again, one hypothesis is spelled like this, with the S-I-S on the end. If you have 2 or more of those, you have hypotheses, S-E-S on the end. So again, this is a great strategy then for approaching a 2-column proof. Working forwards until we get stuck, and then we may have to work backwards from the conclusion. Remember, you can relax because you know what the answer is going to be. It's not like some math problems where you have no idea what the answer is going to be at the end. You know the answer is going to be what you're trying to prove. Let's take a look at a couple actual proofs and see how we can apply all that we've been talking about in this lesson. Let's first of all start with something more familiar and more comfortable with, an algebraic proof. Now, we don't have any kind of a drawing here. There's no diagram required for an algebraic proof. This is just a raw algebraic proof just to warm up with. Then next, we're going to do a geometric proof. Well, again, in an algebraic proof, it would be, let's say, like solving an equation. Given a certain algebraic equation, prove from that equation that x equals 6. Now, like I said, there's no diagram here, but we still do have statements and reasons that would follow as we solve this given equation into our final answer of what we're trying to prove. So the only thing missing in an algebraic proof would be a diagram, because it is not a geometric proof yet. A lot of the algebraic properties, however, will be used, in our later proofs. Okay, let's make our 2 columns. First of all, for our statements on this side, and then, of course, our reasons on the other side. Again, learn to help yourself get organized this way. Make it structured. Be neat. Your success on these proofs will be directly related to how neat and organized you are. Your success will be directly related to how neat and organized you can be. And you can train yourself to be organized if you think you're not an organized person. All right, the given statement here, number 1, let's say, is 7 times the quantity x minus 3 equals 5x minus 9. That is given. Okay, so that's our beginning statement and proper reason. That's the given. To solve this algebraically, by the rules of algebra, we would use the distributive property. 7x minus 21 equals 5x minus 9. That would be our next statement. In other words, open this thing up. Remove the parentheses. We've got to get this thing out in the open. And again, the reason we can do that is the distributive property. Of algebra. Then next, we've got to combine our x terms together on one side and the number terms together on the other side. So let's move the x terms together on this side. And how we can do that is that we have subtracted a 5x from both sides. We have the right to subtract that. So that is by the subtraction property. Then next, we want the numbers all together on the other side. So our 2x would be left alone over here, and we'll get 2x equals 12 when we add this 21 to both sides. So that again is the way we get our x terms to one side and the number terms to the other side. This is by the addition property. And last of all, we don't want 2x. We've got to, remember, have our answer as just 1x. So we would divide both sides by 2 to get just 1x. So x finally equals 6. And what we did here was to divide both sides. So that is the division property. So there is a simple algebraic proof, basically how we're solving an algebraic equation. Now, let's take a look at a geometric proof. I'm going to go back and prove a theorem. This is actually theorem 2-10 by my numeration system. Vertical angles are congruent. Well, again, this is the given. We have given that we have vertical angles, so draw them accordingly. Draw vertical angles. And let's number them. We'll call that 1, 2, and 3, like so. All right, these are vertical angles right here. So it's given that angle 1 and angle 2 are vertical angles. Okay, again, draw it accordingly. Make it look like it's supposed to be. We're trying to prove that they are congruent. It's given that they're vertical angles. We're trying to prove the final conclusion here at this sentence that they are congruent. So we're trying to prove that angle 1 is congruent to angle 2. Okay, so there's the proof, what we're trying to be given. In other words, given that they are vertical angles, we're trying to prove this theorem that they are, in fact, then congruent. There's our diagram. We're next ready for the statements. And then the following matching reasons. Okay, now, drawing from our definitions and other properties and postulates and theorems, we have to reason deductively forward through this proof. First of all, write down the given. Angle 1 and angle 3 are a linear pair. When you look at your drawing, see, the drawing would help you jog your memory as to what is there. You can look at those and say, well, hey, those are a linear pair of angles. They are a linear pair because of the definition of what a linear pair is. Two angles that are adjacent angles whose non-common sides are opposite rays are a linear pair of angles. Two adjacent angles whose non-common sides are opposite rays are a linear pair. Now, that's leading us to relationships of angles and measurements and so forth, so that kind of jogs our memory to say then that therefore the measure of angle 1 plus the measure of angle 3 would equal 180 degrees, since they are a linear pair. Oh, and by the way, we've got to connect these to 2, so we need to say up here that also angle 2 and angle 3 are a linear pair. So if you did not remember to write that down in the first place, you see you can kind of go back because you've got to have them connected here. You've got to connect angle 1 to angle 2. So you have the right to go back. That's part of the drawing. So therefore, the measure of angle 2 plus the measure of angle 3 also equals 180 degrees. Why? Because if two angles are a linear pair, then the sum of their measures is 180 degrees. Again, if two angles are a linear pair, I'll abbreviate LP for now, linear pair, then they have a sum of 180 degrees. So we converted this idea of the drawing into linear pair on into numbers, 180 degree sum. So look, these two sets of angles each equal 180 degrees. Well, that means then, if they both equal to 180, wouldn't that mean that angle 1 plus the measure of angle 3 equals the measure of angle 2 plus the measure of angle 3? Why? Because they both equal the same number. That's by then substitution. Substitution property. They both equal the same number, 180, so they could be set equal to each other. Then, again, remember what we're trying to do here. Keep focused. Look at what we're trying to prove. Where am I going with this? We're trying to prove that angle 1 and angle 2 are congruent. I've got angle 1 on this side. I've got angle 2 on that side. But angle 3 is in the way. But I could take angle 3 away from each side. I can subtract the measure of angle 3 from each side. So that would leave me with the measure of angle 1 equals the measure of angle 2. That is by subtraction. The subtraction property. Now don't abbreviate subtraction and substitution because they both would be possibly abbreviated SUB, and that might get confusing. So if you abbreviate those two words in your proofs, write it out as SUBST for substitution and SUBTR for subtraction. So don't abbreviate just SUB because that could be the substitution or subtraction. So if the measure of angle 1 equals the measure of angle 2, then in conclusion, angle 1 must be congruent to angle 2 because of the definition of what congruent angles are. The definition of congruent angles are two angles that have the same measure. In our next lesson, we're going to be talking about parallel lines, identifying parallel lines and how they relate to angles, related angles, and planes, and even the three-dimensional world.